In the last module, we started doing the derivation for transforming the ordinary partial differential equation to an ordinary differential equation. We started with the stream function definition and said let the stream function therefore be given by some z of eta bar times some n of x. Okay. So, now you might ask, or students may ask, how do you know that this is what is going to work? It is a very pertinent question, but one must remember that many such manipulations would have been tried over several years, several months by several people, and you can have varying transformations, varying possibilities, but ultimately only one of those would give us a similarity solution. By you will understand the impact of this statement once we finish the derivation. I can have any transformation which comes to my mind, but whether it will transform the PDE to an ODE and therefore ensure similarity is something which we cannot decide. Once I choose the function, I do not know whether it is going to be able to satisfy the condition of similarity. So, there will be additional constraints imposed once we choose the function by the final form of the equation, ordinary differential equation, which would result in certain conditions which you will not be able to satisfy at all. Therefore, those transformations which you thought of may not work. Based on that, what is being presented is a formulation that works. Okay, so this is something which you have to keep in mind. Oh, how did somebody think like this? It's not that it came off in one day or sitting and just thinking, okay, this is what is going to work. It doesn't work that way. It would have been several years of thought processes, several failures. Ultimately, this one particular form, of course, there is an underlying mathematical intuition which is there. Okay, so coupled with these two, you are going to have a transformation possible. Okay. So, it is not something which just fell off like the apple falling off of a tree or something like that. Okay, we stopped at transforming the stream function second derivative. Now, we say we want to do the same for d cubed psi by dy cubed. Why? Because my equation here, Navier-Stokes equation, has these three terms. Remember, 1, 2, 3 terms, and of course, you have this fourth term. So, these are all written in terms of the stream function, and therefore, I would want to transform this to d cubed z, and instead of x and y, I need a eta bar. So, my z and eta bar should take care of psi x y. This psi was actually u and v. So, u, v, x, y should be now replaced, all of them be replaced by z and eta bar. That is the bottom line we are trying to get at. Okay. We had written the expression for d squared psi by dy square. So, let us write it now in a form which is going to be useful. D squared psi by dy squared is now u infinity divided by n d squared z by d eta bar square. This is nothing but u infinity squared by n, both of which are functions of x, d squared z by d eta bar squared, or if I want to write it, it is going to be u infinity of x squared divided by n of x d squared z by d eta bar squared. Next one, we have d cubed psi by dy squared, because that is what is there on the right hand side of the Navier-Stokes equation. Right hand side of the Navier-Stokes equation, which was basically this term, has this. So, we want to transform this to z and eta bar. So, this is z and eta bar. We are going to write this as d by dy of d squared psi by dy squared. D squared psi by dy squared we got here, and this is nothing but d by d eta of u infinity squared by n d squared z by d eta bar squared times d eta bar by dy, which is nothing but This will become third derivative. This is nothing but u infinity by n. So, I would get this as u infinity cubed divided by n squared d cubed of z divided by the eta bar cubed. So, please keep this in mind. Let us keep this in mind as the second part. Now, I will write the third one for v. Velocity v which we need is minus d psi by dx is equal to minus d by dx of z eta bar into nx. Right? Stream function definition, we have chosen it exactly that way. So, I am just substituting for stream function definition. So, this, if I open the bracket, product rule of differentiation, this is going to be nothing but you are going to have minus as it is z of eta bar dn by dx plus n of x dz by d eta bar by dx. This is my v. So, we will retain this for later use, and lastly we need d squared psi by dx dy is nothing but d by dx of d psi by dy. D psi by dy was nothing but u, and what was u? By definition, this is u. This was our definition of u. U infinity times dz by d eta bar. So, I am going to substitute for that here. So, this is d by dx of u infinity which is a function of x dz by d eta bar. This would become u infinity d squared z by d eta bar squared d eta by dx for this term, keeping u infinity as constant, plus dz by d eta bar regular derivative du infinity by dx, because u infinity is only a function of x. So, this is the part here, this is my v. Now, we will introduce all this into the Navier-Stokes equation. The Navier-Stokes equation we had essentially was having these things. Left hand side u du dx was this, v du dy was this, u infinity retained as it is, nu d squared u by dy squared was this. We have written expressions for all these three terms. See here, d squared psi by dx dy, d squared psi by dx dy, we have an expression. D cubed psi by dy cube, which is here, we have an expression. So, we are just going to substitute all these. Now, finally, so u into du dx. So, u du by dx is nothing but u infinity dz by d eta bar. This is for my u, and du dx was nothing but d squared psi by dx dy, this bracket. So, d squared psi by dx dy has been written by me already. D squared psi by dx dy has been written by me here as u infinity d squared z by d eta bar squared d eta bar by dx plus, I am merely copying it from the previous slide, okay, du infinity by dx. This is the first term. Second term is plus v du by dy. What is that? V has a big expression here. So, I just have to copy the expression for v, and then du dy is this term. So, I am just going to write this minus, because this v has a minus sign, z of eta bar dn by dx plus n of x dz by d eta bar, d eta bar by dx. This is my v. This is my u. Okay, this is my v. Du dy was d squared psi by dy squared, and I am just going to write this as u infinity squared divided by n d squared z by d eta bar squared, directly taken from here. Right hand side equal to u infinity du infinity by dx. I am just retaining as it is. So, I am just writing the original form of the Navier-Stokes equation. This is the modified form, u infinity du infinity by dx. This is just going to be retained this way, no change, plus nu d squared u by dy squared. That term is going to be given by nu d psi cube by dy cube, that is written as plus right hand side this is. So, right hand side is nu u infinity cube by n squared d cubed z by d eta bar cube. Please note n and eta are different, make sure you write them differently. Eta has a long tail, n does not have a tail. So, if I do this maths, simplify, and just for simplification let us call z prime is equal to dz by d eta bar. This is just notation, nothing else, and this is a conventional notation, and we do the algebra, we get the governing equation as u infinity du infinity by dx into z prime squared minus dn by dx u infinity squared by n z double prime is equal to u infinity du infinity by dx plus nu u infinity cubed by n squared z triple prime. Just using this notation and simplifying, you will cancel off a few terms because of this simplification. For example, u infinity squared d squared z d n squared d eta by dx, this term would cancel. N of x here would cancel with this n of x. This has a minus sign, this has a plus sign. So, several terms will cancel, and this is my simplified Navier-Stokes equation. Very good. What is the big deal now? This has now become an ordinary differential equation. In z, we have z prime, z, z double prime, z triple prime. What is this? This is only a function of eta. This is ordinary differential equation. Is this useful? Not exactly. So, we first anyway will specify the boundary conditions at y equal to 0, which means eta bar equal to 0, u equal to 0, which means z prime of 0 is 0. You might be wondering, what am I writing? Well, y equal to 0 corresponds to eta bar equal to 0. At wall, u is equal to 0. What is u equal to 0 means z prime of 0 equal to 0. That is what I have written here. Okay. Please remember my definition of z prime of eta bar is u by u. Keep this in mind. Okay. This is what is feeding into this. Then I have at y equal to infinity, or y tending to infinity, that is eta bar tending to infinity, u is equal to u infinity, or if I want to write z prime of infinity is equal to 1. Third boundary conditions at y equal, how many boundary conditions do I need? It is a third order ordinary differential equation. So, I need 3 boundary conditions. 2 are very obvious. Third one is at y equal to 0, that is eta bar equal to 0, v is equal to vw of x. This is not coming in terms of eta. This is not coming in terms of eta, as you can see. This has to be written in terms of eta. Write in terms of z. Vw is not so useful for me. So, we are going to do that manipulation right now. So, Vw of x, we wrote, if you remember, V is this. So, we are just copying that expression now and saying Vw is given by minus z of eta bar dn by dx plus n of x dz by d eta bar d eta bar by dx. This is V. This is your expression for V. Expression for V is this. We have copied from earlier slide. This is not derived now, copied from the earlier slide, it was derived earlier. So, when y equal to 0 or eta bar equal to 0. So, when eta bar equal to 0, what are we trying to say? Dz by d eta bar is equal to 0, which is no slip. That means u equal to 0. Please remember my definition of u. Eta bar at 0 is u equal to 0. Where does it occur? This one. This one is here. Therefore, Vw is equal to minus z of 0 dn by dx, which means z of 0 is equal to minus Vw, which is a function of x, divided by dn by dx. This is my third boundary condition. Remember, I needed 3 boundary conditions. First one was z prime of 0, second one was z prime at infinity, third one z of 0, which is nothing but the suction or blowing velocity divided by some quantity dn by dx. So, now I just manipulate this ODE. So, divide the ODE both sides by, I want to keep this out, I need z triple prime only. So, if I want z triple prime, I will divide by this quantity. So, divide everywhere by nu u infinity cubed by n squared. Therefore, after division I get ODE is this one, where beta 1 and beta 2 are going to be written here for you. So, where beta 1 and beta 2 are going to be written for us as beta 1 is nothing but, so beta 1 is nothing but this quantity, beta 2 is nothing but n squared nu u infinity squared du infinity by dx. This is beta 2 and beta 1 dn by dx n nu u infinity. These are what your equation, this is what your equation is going to look like. Third order ordinary differential equation in eta bar, dependent variable is z. We have 3 boundary conditions, z prime of 0, z prime at infinity, z of 0. Technically, this is solvable. What is the problem now, or what is the constraint now, is what we will see in the next module. This beta 1 and beta 2, which are not so straightforward, which look like some expressions, will have to take some specific form, so that this equation which we have derived is truly an ordinary equation. More on that in the next module. Thank you.